Section 2C is about problem solving. Problem solving is going to be one of the harder sections for this unit. We'll take it a little slow at first. Some of you might want to go a little faster. That's fine. You can skip through the video as quickly as you want. But I do suggest, like previously, please read the section beforehand so that it makes a bigger impact and you know what to look for in your questions throughout the lecture. There are 4 steps to the problem-solving process that help break down how we can work these out. The first step is understand the problem. Read it, and read it several times if necessary. Those of you who are auditory learners, go ahead and read it out loud to yourself. It'll help if your roommates or people around you think that you're silly, then maybe even mouth the words. You can make a list or a diagram or a picture or a table, whatever helps you visualize what's happening. I'll tell you that my strategy is usually a diagram or a picture. I'm a visual learner, so that works for me. You can also restate the problem and make a model of the solution. The second step is devise a strategy. So you can make a list of strategies. You don't have to write them down, but think of different things that might work. And then obtain information not provided. So maybe make a couple of calculations if it gives you some dimensions, and map out which strategy you would like to use. The third step is carry out your plan. Write everything. I know it's a little hard because we're on the computer, but don't erase things. Keep it all written, typed up, and double check and revise everything if not, so that you can make sure that your work is perfect. And the last one is check, interpret, and explain your results. Make sure that your answer makes sense. We just covered the unit in this last section in units, so make sure that your units are correct. Does it make sense? Did it ask for how much and you got inches? Well, then that doesn't work because you needed dollars. And then recheck your work and circle your answer, but in our case, use a highlighter or a different color or bold it some way. You could even insert a shape like a circle. If you have a computer that has an inking program, you can go ahead and do that to circle your answers that way. That's up to you. All right, let's move on. Hint number 1. There may be more than one right answer. For example, if you have the question, how can we best reduce the amount of greenhouse gases emitted? There's lots of different options and everyone definitely has their opinion. The next one is, if I have tickets for a fundraiser that are priced as follows, children are $10 and adults are $20, and we have the question that Sally has worked a shift at the box office that sold a total of $130, but she didn't keep track of how much of each ticket she sold. How many options do there's lots of different options to figure out how many adults versus children tickets. Excel is a fantastic tool. In fact, this is how I've solved it here. In fact, let's go ahead and go into Microsoft Excel. So those are left over from the last section. Here, let's call this the number of adult tickets. And then we're going to do some calculations and we'll need to know how many children tickets. Remember, the adult tickets are $20 and the children tickets are $10 with a total of $130 sold. So over on this side, we're going to do the number of adult tickets. There is a possibility that I have 0 adult tickets, 1 adult ticket, and so on and so forth. Now, I'm going to show you a cool trick with Microsoft Excel. If I highlight a pattern that's occurring, and then down in this right-hand corner, get my crosshairs, I can take it down and it will continue my numbering for me. Now, I don't know where I need to stop, so I can go as far as I want for $130. So, over here, now I'm going to start calculating something. If I have 0 adult tickets, and I know this is going to sound a little silly to have 0 here, but we're going to create a pattern because we're using Microsoft Excel or a formula. So I want $130 subtracting the 0 adult tickets times the $20 that it takes for an adult ticket, and I'm left with $130. Now I could go ahead and do it again on number 1, but Microsoft Excel, as you've noticed, if I take these crosshairs, it will take that formula down with me, and I notice that right here I go beyond 0, so I'm going to delete those ones, and when I pulled my crosshairs down, I have 130, and it used the cell to the left of me and multiplied it by 20 to give me 110, and it continues down to here so that it followed my pattern. Now that I have how much money I have left over for each one, I come over for the number of child tickets. So here I'm going to create another equation by pressing equals and going to the money left over and dividing that by the price for a child's ticket is $10, and I would have 13 children's tickets. I could do the same thing again by typing in 110, but Microsoft Excel will continue that pattern. And if I double click in here, you'll see that it used my $50 over here. Divide it by the number of children's tickets will give me 5 children's tickets. Those are all the different combinations. So that was for hint number 1. Coming back, there we go. So I did an expanded version of the Microsoft Excel that we did so that you can see exactly what we did for each one. We did 130 minus 0, $0, 130 minus 1 adult ticket, 130 minus 2 adult tickets, and so forth. And then we're left with $130 divided by $10 will give me 13 children's tickets. All right, let's move on to hint number 2, or Roman numeral 3. There may be more than one strategy. Jill and Jack ran a 100-meter race. Jill won by 5 meters. Jack had run only 95 meters when Jill crossed the finish line. They decided to race again, but this time Jill starts 5 meters behind the starting line. Assuming they run at the same pace, who will win the second race? We have different ways to, we all have different learning styles, and there's different ways that you may approach something. You can be creative, you can be analytical. I'm a very visual learner, so I draw my way through all story problems. Sometimes I use tactile objects too. Those of you who are a tactile learner, if you need to see Jack and Jill running, get a pencil in your hand and a pen in the other, one's Jack and one's Jill, and make them race to see what's happening. Also, you auditory learners, feel free. Read this out loud to yourself several times. Just maybe explain to others that you're reading a problem. Okay, here's Jack and Jill. I am visual, so I created a visual for me. Jack is going to be running, and Jill runs the full 100 meters, and Jack only got to 95 when Jill ran, or crossed the finish line. So the first thing I would like to do is run through some equations. Rate times time equals distance, or distance equals rate times time. And then I can divide both sides by t and get the rate is distance over time. Or I can divide both sides of my original equation by r and get time equals distance over rate. If you're having a hard time doing that really quickly, go ahead and pause the video and then come back after you've solved that by dividing both sides by t or r. All right, since it didn't tell us the time that Jill finished the race, we're just going to pick something. We're going to just say she ran in 10 seconds. It doesn't really matter in this case how long it took her, because the time isn't what we're looking for. We're looking for who's going to be faster. So if I want to find how fast they are, that's a rate. So I take distance and divide it by a time. And we picked a time, 10 seconds. Just arbitrary. So Jack's speed is going to be 95 meters over the 10 seconds because that's where he ended at 95 meters when Jill finished crossed the finish line. And that gives us 9.5 meters per second. Jill's speed is rate equals distance over time. She finished the full 100 meters. divided by 10 seconds. She ran 10 meters per second. Now we're going to take their rates and figure out who would win the second race. So the time that Jill will take is so we'll come up to our time, distance over rate. Jack will go the full 100 meters. He starts right at the end, and his rate is 9.5. How long will that take him? You can plug that into your calculator, or you can go into Excel and do 100 divided by 9.5, and we will get 10.5263 seconds. And I'm going to go ahead and highlight that so that we know what the answer is. Now, Jill's starting 5 meters before the starting line. So she's not going to be running a 100-meter race. She's running 105. So her time is going to be distance over rate. So her distance is 105 meters divided by 10, and she will finish the whole 105 meters at 10.5 seconds. Now let's compare. Who ran to the finish line the fastest? Jill still won by, in this case, 0.263 seconds. So she wins no matter what. Now, why is that? She started 5 meters behind. Let's move on to the second strategy. This one is just intuitive. We didn't do any calculations. So if Jill won at the same time in the first race, she won the 100 meters when Jack hit 95, then she will pull even with Jack on the second race at 95 meters. So here's the starting line, but she's starting 5 meters behind, and she ran at the same time she hit 100 meters, Jack hit 95. So here's her 100 meters. She will have the exact same time as Jack in his 95 meters. And we really only have to compare the last 5 meters of the race. So we ignore all the first part and say who's going to run the last 5 meters faster. Well, Jill's a faster runner, so she's going to pull ahead in the last 5 meters. That was a lot faster than the first one. Use whatever tool best suits you. You could come up with something else, maybe using Excel to make a diagram. Okay, hint number 3, using appropriate tools. If I have 2 cars that are 120 miles apart and are driving towards each other, one at 20 miles an hour and the other at 40 miles an hour, a genetically altered canary is atop the hood of one of the cars and starts to fly at the same time back and forth between the 2 cars. The little yellow bird can fly a whopping 150 miles per hour and can turn instantly at each car. How many miles does has little Tweety flown by the time the 2 cars crash? So you've probably seen these kind of problems before with 2 things coming towards each other, and when do they crash? But now we throw in this added twist of this teeny little bird who can fly faster than the cars. So I can either try and add up every single distance as this little canary flies, and notice that each length is a little smaller because the cars are constantly approaching each other, and this poor little bird, I'd have to add up all of these distances. But there's a faster way. Remember, rate times time equals distance, or distance equals rate times time. Time is distance over rate, and rate equals distance divided by time. Just keep these on hand. I'm going to highlight those. Keep those on hand for these problems. So if I have the 2 cars approaching each other, one at 20 and one at 40, the total car speed altogether that this little canary has to race against is 60 miles an hour. Now that I know how fast the cars are approaching each other and how little time that gives the canary, wait a minute, we just said time. What if we find how long the canary flies in between the 2, going the 60 miles with the cars approaching each other at 60 miles per hour? If I take this 60 miles per hour and use my 120 miles between the 2 cars, that's a rate and a distance, I can find time. Distance and rate, time is distance over rate. So if I take 120 divided by 60, I'll get the time that these 2 cars crash. So there we go. Using our unit conversions, or what we learned in unit conversions, time equals distance over rate. So I have 120 miles over 60 miles per hour. I have to flip and multiply. So this becomes 120 times 1 over 60, and these will be flip-flopped with miles over, or hours over miles, and the miles will cancel out. And now the hours will be on the top because you flip and multiply, and I'm left with hours. 120 divided by 60 gives me 2 hours. So in 2 hours, these two cars will meet, and this little canary can only fly for 2 hours. Okay, so now I have the canary flies at 150 miles per hour, and he has 2 hours to fly. So I have time and rate. That will give me distance. Rate times time equals distance. So I can take my 150 miles per hour, times it by 2 hours, and I will be left with a distance. So 150 miles per hour that this little canary can fly, times it by 2 hours, using unit conversions that we did previously. One of the hours is on top, one is on bottom, so they cancel out, and I'm left with miles. 150 times 2 gives me 300 miles. And highlight it in some fashion so that I know that's your answer. So it kind of breaks it down and makes it a little easier to digest a little bit at a time. Hint number 4, simplify the problem. So we have 2 cups. One cup is full of water, the other cup is full of milk. If we take a spoonful of milk and mix it into the water cup, and mix it up really good so it's a kind of milky water, then take 1 spoonful of this milky water mixture and mix that back into the milk. Is there going to be more milk in the water cup or more water in the milk cup? Or is there an equal amount to both? So those are my 3 options. There's either more milk in the water, more water in the milk, or there's equal amounts. It's kind of hard to wrap your head around, so let's think of it in a simplified version and just use, let's say, marbles or dots or circles. So here I have my stack of blue marbles and my stack of orangey marbles, and we'll make this water and this milk. And I want to see how, let's just say two marbles will be equivalent to a spoonful. So I'll take 2 marbles, mix it into here until I have a mixy, watery concoction. And then I have 2 marbles going back because the problem said I take a spoonful of one, mix it up, and then take a spoonful. They are equal spoonfuls, so I take 2 marbles. I have different options of my 2 marbles. I could take my 2 blue marbles. I could take an orange and a blue marble, or a blue and an orange, same difference, or 2 of the oranges, and mix it back into this one. If I do that, so these 2 are gone, they were mixed in over here, I have these options to put into this one. If I take the 2 blue marbles and put it back into this pile, then these are all blue and these are all orange. It's the same amount. If I have 1 blue and 1 orange, so I've taken 1 blue and 1 orange, I'm left with 1 blue on this side. Taking my blue and orange and adding it to this, I have a blue and an orange. There's only 1 orange in that section, so I have 1 orange here and 1 blue here. It's equal amounts in that one. Now let's go ahead and see what happens if I take 2 oranges. If I take 2 orange marbles and move it into this pile, I have an orange here and an orange here. There are 2 orange marbles in the blue pile, and over here these 2 blues stayed, and I have 2 blues in the orange pile. I have equal amounts. No matter what kind of pairing I use, I will have the same in both. So the answer is there, because it is equivalent with the marbles, it'll also be equivalent in the milk and water example. There's my answer. Tactile learners, go ahead and use something. If you're having a hard time visualizing this, go get a little stack of marbles or whatever you have on your desk, or if you're whatever's close by, use those and move them back and forth and see what you get. You can do that on homework and the test too, and that'll really help. All right, hint number 5. Consider equivalent problems with similar solutions. Suppose you're decorating for a party that has 10 cylindrical pillars that are 8 feet tall and have a circumference of 6 feet. You would like to wrap each of these posts 8 times with a ribbon. How much ribbon will you need? So I can think of it as a circle and try and figure out the circumference. Or I can, in my mind, cut these pillars down one side, kind of like a toilet paper tube, and open it up flat, and I have a rectangle. And because I'm wrapping it up with my ribbon, it ends up creating a diagonal, which ends up being the hypotenuse of a perfect right angled or right triangle. Now, how do we find the length of a hypotenuse? A squared plus b squared equals c squared. And I can find the length of 1 by using the Pythagorean theorem. And then all I have to do is multiply it by, how many times are we wrapping around? 8 times. So here we go. It told me that my cylindrical pillars are 8 feet tall, 6 feet in circumference, so the length of my rectangle is 6 feet, and because it's 8 feet tall and I want to wrap it 8 times, it means between each wrapping is 1 foot. So my dimensions of this right triangle are 6 feet by 1 foot. So I have 6 for one of the legs of the right triangle, 1 for the other right leg, and c will be the hypotenuse. So I have 6 squared plus 1 squared equals c squared, which gives me 36 plus 1 equals c squared, or 37 equals c squared, and the length of that ribbon will be the square root of 37, or 6.1 feet. Now, that's only one of these hypotenuse, and I have 8 per pillar, and I have 10 total pillars. So I'm going to need to multiply that by 8 per pillar times 10 pillars, which gives me 6.1 times 8 gives me 48.8 feet for one pillar. Now I need to multiply it by 10 different columns. So 48.8 feet times 10 gives me 488 feet of total ribbon needed to decorate all 10 pillars. Now, you'll notice I gave you a couple of leading questions. A lot of times, somebody will solve the problem that they've worked on so long to find the length of the hypotenuse for the ribbon here and think that they're done. In reality, you need to keep going. Ask yourself these questions as you're moving along. So often on a test, somebody will stop too early, and go back and make sure you answer the question. How much ribbon will you need for the entire project? So I needed to multiply to find how much would be on one pillar, and then I have 10 pillars, so multiply it by 10 for the total number, or the total footage of ribbon needed. Hint number 6. Approximations can be useful. Here is a bridge problem. I know in your book you have a railroad problem. Both of these are actual real-life problems that have occurred. So we're going to talk about bridges first. Bridges normally have expansion joints built in so that as the materials change from the heat, it can be absorbed without disturbing the surface. Because when something heats up, like metal, it expands. They actually had big problems with this in railroads. You know the clickety-clack sound of a rail? That happens because they're cut into sections so that it can expand and contract according to the heat and the weather. But let's suppose a bridge could be built with a rigid material so that the expansion is absorbed by a hinge action in the middle of the bridge, and then the ends are firmly anchored, just kind of like a railroad. So it's anchored a mile apart, or 5,280 feet, and the middle portion of the bridge moves up. So I have a coefficient of expansion of 1 over 2,640. The bridge surface would increase by a length of 2 feet. So how high would the center of the bridge be at its maximum expansion? And a little extra question, would a person who's 6 feet tall be able to see another person 6 feet tall on the other side of the bridge when it's at its maximum expansion? Your problem in the book is a railroad, and a railroad is going to bow instead of having a hinge action. So it's a slightly different problem, but the same concept, and it's pretty fascinating. If you want to go see a little bit more, you can go here. All right. So we're going to use a right angle to estimate the height of our bridge. In this case, it's going to be the actual height. In your book, the railroad is bowed, so it's going to be a little smaller, but we're using the same problem. So if I have 5,280 feet between these 2 points, then from the middle out, it will be 2,640 feet from the middle to one of the ends. We want to know how high it is. Now, if it's 5,280 feet long and it expanded in length by 2 feet, then I already know the hypotenuse in this one because I have 2 feet longer. So I have 1 foot of length on this side and 1 foot of length on this side. Using our Pythagorean theorem, we'll have one leg, 2,640 feet squared, plus the height squared will equal the hypotenuse squared, 2,641 feet squared. So I have that all plugged in down here. Now we want to solve for height, or x squared or h squared. When I square this, I get this number, and when I square 2,640, I get this number. Subtracting that from both sides will give me x squared equals 5,281 feet. Then I need to solve for x, or the height. Square rooting both sides gives me the square root of 5,281. Plugging that into your calculator or into Microsoft Excel, you get 72.67 feet. That's the height of the bridge. If this were to expand only by 2 feet, it would be 72 feet tall in the middle of the bridge. So our extra question, would a person 6 feet tall still be able to see a person 6 feet tall on the other end of the bridge when it has expanded its 2 feet? If it's 72 feet tall, absolutely not. Amazing, isn't it? This was a big problem, and engineers have found different ways of combating that problem. All right, hint number 7. Alternative thought patterns. All right, alternative thought patterns are more like aha problems. In 1978, China instituted a policy that allowed only 1 child per family. One of the unintended consequences that has happened because of this, and because of the cultural bias towards sons, China now has many more males than females. This is due to abortions or other cases. As of May 2013, an infant was just discovered in the sewer pipes in China. Some have suggested that abandonments like this are linked to China's one-child policy and its strict rules and heavy fines for parents who breach that. So, what if China changed their policy to be a one-son policy instead of a one-child policy? What would that do to China's population? I like to do this one visually, so I can either line up all of these males on one side and all of the females on the other, and just think of this as every single baby that would be born in China. Half of them are male, half are female, because it's half and half. Now, the families that get their one boy in the first set, that very first child, they're done. So no more babies underneath. Those over here who have a girl first get the option to have another child. So this is the next line of representing the second child. Half of these children will be boys and half will be girls. And the families over on this side have now had their one son, and they are done. No more children below. These families below who got two girls in a row still don't have their son, and they're allowed to have another. So from here to here, my visual is half of these are going to be boys and half are girls, and so on and so forth. And it keeps going. But what does that look like compared to the one child policy? So what I like to do is rearrange these a little bit by moving up these different blue segments and connecting them together, and the different pink segments connecting them together, and what do we get? All of these blue children, or children had, all of these families had a son first, and then I compare it to all of these pinks. There we go. It all lines up to match perfectly. Same with this side. If I rearrange the blues and just slide those up and compare, it ends up being that there's only two children at every point here. And that's exactly how it averages out. So if they were to change their policy to be a one-son policy, it would be two children per family. That's what it would average out to be, versus the one-child policy, and it also balances the genders. So you wouldn't have as many infanticide and abortions of the female gender. All right, which policy would be better for China? I definitely feel the one boy policy would be better, and we just discussed why that. Number 8, don't spin out. Let up on the gas and take a break, and then come back to it. In many cases, in my own math classes, sometimes I would study until I couldn't anymore, take a break and go to bed, and by morning, you could figure it out. So make sure that you allow yourself that time. Also, make sure, especially in this section, if things aren't coming as easily, get a tutor. These are online, they're free, it's through BYU Idaho. Just sign up. Good luck, and I'll see you for the next section.